Hey, this is Mr. Justice. We're going to talk about population growth and resource availability. Here's what we will be going over today. All right, so let's first start off our discussion here by getting into population characteristics. One of the first population characteristics that we should know about is size. Size refers to the total number of individuals in a given area at a given time. And in equations having to deal with populations, size is denoted with the letter n. The larger the size of the population, the better that they'll be able to rebound after a disruption. Another population characteristic that we need to know about here is population density. This is the number of individuals per per some unit of area. For example, we've got 12 panthers per square meter. Here in the United States, we have a population density of 36 individuals per square kilometer, or about 94 people per square mile. And you can actually see here the population distribution and the density throughout our country, right? The redder areas here suggest a more dense population, and the lighter greener areas here represent less dense population. You notice here that it's not an even distribution of individuals here throughout our United States, right? You can kind of see that we have this clumped distribution here, clumped around metropolitan areas where there tends to be a lot more access to jobs and affordable housing. Higher density in ecosystems, right? Let's get back into nature. Higher population densities mean more competition for limiting resources, right? There's more chance of transmission of disease the closer individuals are per unit of area, right? Or it even increases predation the more dense a population is. Let's talk a little bit more about some population characteristics that we'll get into here. Gender ratios, sex ratios, the number of male individuals to female individuals. Right, closer to 50-50 is going to be the best, most ideal ratio for breeding. Remember that bottleneck effect, one of these random kind of disruptions here can decrease the sex ratio of wildlife pretty readily and skew that, right? Ecosystem managers, wildlife managers might be interested in sex ratios in order to be able to come up with a plan for conservation of some animal in a specific area too. Distribution is a characteristic of populations, right? How individuals in a population are spaced out in relation to one another. Take a look at the image here on the right-hand side. The first one here is random distribution of individuals. This occurs oftentimes with plants. Think of random distribution of seeds, as the seeds might be carried and deposited by birds or by wind, for example. Uniform distribution might occur with territorial animals, including some birds here that you're seeing. In addition, you might see uniform distribution in plant organisms that release chemicals into the soil. And what these chemicals do, that some of these plants have adapted to do, is to get a chemical into the soil that really prevents other plants from encroaching on its space that it's taking up in soil. You see this with creosote bushes in the desert. If you ever drive through Las Vegas and you look at the wild area, you see these little bushes that seem to be spaced out in equal distances from one another. That's because they're emitting a chemical into the soil that again prevents those other trees, their competitors, from encroaching on their nutrients. And then clumped distribution. We have clumped distribution here in our human population in the United States in that picture that you saw earlier, right? Those metropolitan areas are kind of, clumped randomly about. You're going to see this in the wild too with animals and plants that are clumped around specific resources too, right? Think of nutrients within a soil or a watering hole or proper habitat that is conducive to the growing of these organisms. What are some factors that can regulate the size of populations? There's two different types that we'll talk about, two different ways that we can regulate a population. The first one's called density-dependent population regulation. What is this? This is population size is dependent on the population density. The more dense the population is, the more that these will increase. The more competition for limiting resources will occur, right? There's two types of competition that can exist here in our natural world. First one's intra-specific competition. This is competition among members of the same species. Think of these cattle right here that all might have to compete for the same grass, right? Or the same watering hole. That would be an example of intra-specific competition. If we added another organism into this, maybe like a wildebeest, for example, we now have two different species competing for the same resources, right? The wildebeest and the cattle will both are grazing organisms that will want to get their food from the grass, and so they're going to compete for that too. What are some other ways that populations can be regulated dependent on its density? Access to living resources, right? The water, the food, the habitat, the mates available. Disease and parasites is also a density dependent factor that can really regulate the size of populations dependent on how dense that population is in an area. Think of these cattle right here. These cattle are in close proximity to one another. So if one of them was sick, maybe it had a rinderpest virus in it, it is very more likely to pass on that disease or a parasite to its neighbor, right? The closer, more dense the population is in the area, the more transmission, the more likelihood of transmission of one of these pathogens to these organisms. And it might not necessarily kill the animal, but it could weaken it. Waste accumulation is another density-dependent population regulation factor here that can limit population size, right? The more individuals in an area, the more waste they produce, the more likely you'll probably transmit one of those diseases, right? Or take up habitat space, for example. I mentioned earlier that one of these organisms here might actually, get sick. It doesn't necessarily always going to kill the animal, but think about this. If one of these cattle here were sick, it's going to be easy prey for a predator that might want to pick one of these individuals off, right? Going after the unhealthy or the weaker of the individuals. In fact, predation is actually a good thing in that it weeds out some of those individuals here, those unhealthy individuals, weeding them out of the population and making that population actually stronger as a result. Take a look here at the predator-prey relationship. We're going to follow these numbers here on our graph. First step here is that the hare population, the prey population is going to increase because there's nothing controlling it, right? Or there's not as many controlling it. That's the predator in this case, right? The green line. So if the hare is the purple line, the green line here represents the predator, the prey. So take a look, right? First, we see an increase in the prey because there's nothing controlling. There's not as many individuals controlling that population. So the prey population increases. Well, take a look at the next step here. The lynx population, the predator population, will increase then too because there's now an increase in the food available for the area. So we're increasing the access to those limiting resources for one species, and we're going to see them increase in population size as a result, right? More food means more prey, means more predators, and the predator population increases. Take a look, step 3 here. Increasing lynx population will limit the hare population. This leads to a die-off. Now all of a sudden we have more predators. Those predators can start eating a little bit more. When they eat a little bit more, that's going to start to drive that population size back down of the prey. That hare die-off decreases the lynx food source, which leads to a die-off then for the predator too. And then it starts all over again in this kind of cyclical oscillating process. Notice that there is an increase here with the predator first, followed by an increase, let me say it again. There was an increase in the prey population first, and then an increase in the predator population second, and then followed by a crash, and then a second crash. And they kind of oscillate around these two extremes until some other thing can stop it. Like, what could stop it? Well, hey, maybe the wolf population gets so high, all of a sudden now we have a lot denser population in an area, more likelihood that we can transmit a disease like maybe something that could, a virus that could impact these wolves here. Hey, That's a density-dependent factor that can decrease wolf population. Look what happens. So the wolf population here in the 1980s crashed. As a result, we no longer have as much of those prey that are being controlled by the predators, right? You see that purple line here of the moose really skyrockets pretty readily here. Probably all the way up until it no longer has access to some of its limiting resources, food, habitat, right? A lot more competition, which is going to lead to maybe some starvation and some die-off too. All right, take a look at this. Remember our populations here that have high biotic potential, those are those R-selected species. Oftentimes we'll see exponential growth, and we're looking at a nice exponential growth model here on our screen. We'll call this line a J-curve. This is growth without limits. Remember, individuals that have high biotic potential, this is the maximum growth rate, population growth rate available under ideal conditions. We'll see that exponential growth. We'd like to see that exponential growth, but in reality, like think about this, we don't have always ideal conditions, or we don't have unlimited resources here, right? Think about this. Our resources here on our Earth are finite. As a result, yeah, we will have some exponential growth in the very beginning, but in reality, there's going to be this like limit to its growth, right? Because there's a limit to the resources available to them. Environmental resistance will push back down against that growth rate of a population, slowing it. So you see that this J-curve here just skyrockets in exponential growth. Well, in reality, we'll see something called logistic growth. This logistic growth model here shows initial rapid population exponential growth, right? But then environmental resistance will slow down that growth so that it's at a plateau, right? Competition is one of those ways that we can decrease it too. Exponential growth may occur initially, but environmental resistance slows the growth limits population size to carrying capacity. Right? What is that environmental resistance? Again, it's that competition for those limiting resources. Take a look here. K is the letter that we use to represent carrying capacity. And so take a look at this population here. Hey, population in the very beginning shows exponential growth, sure, but reality takes over, right? Resources are finite, competition for them increases, and that slows the population to a crawl. And right around that area then is the maximum number of individuals that this specific ecosystem can handle. We'll call that carrying capacity. What are some other factors that can regulate the size of populations? If density-dependent factors can regulate populations dependent on the population density, well, you can also have density-independent population regulation. This is when the population size is controlled by natural events, those natural disruptions, right? Other than population density. Think about this for a moment. A wildfire is going to impact a population of deer in a forest regardless of how many deer there are, right? You can have 1,000 deer, you can have 2 deer. It doesn't matter what the density of the population is, a wildfire is going to decrease that population, right? What are some other natural disruptions here on our Earth? Floods, earthquakes, hurricanes, volcanoes. All of these will impact population size independent of the density, the population density of those individuals. Drought, right? Access to water, absolutely, will decrease population size independent of population density. So take a look here. How can we calculate population size? Or change rather, right? So take a look. So if n, population size n, is right here in the middle, we have some different inputs into our system here that can increase the population size, right? Stuff like immigration and births. Both of these will increase the number of individuals in a population. There's also factors that will decrease population size too. Outputs, we'll call them. These outputs include emigration away from areas and deaths. Both of these decrease. So if one increases and the other decreases, we might see an increase or decrease in our population size as a result, right? It kind of depends on which side is larger. If the input side is larger than the outputs, then our population goes up. If the outputs is larger than what goes into the system, then our population size will decrease. Let's take a look at what the formula might look like, right? Population size N is equal to immigration plus births minus emigration plus deaths. Let's plug these into, let's look at a sample problem here, right? Hey, an elk population of 52 elk has 19 births and 6 deaths in a season. 5 new elks immigrate in and 0 elk emigrate from the area. What's the total population size? Well, let's take a look. Right? We'll plug those numbers into our equation. N is equal to 18 elk. It's a positive number, and so we're increasing the population. Now remember, we had a beginning population size of 52 elk, and so we'll have to add that 52 elk to the 18 total extra that we'll have for this specific year, and we'll get a total of 70 elk. There you go. All right, so where are we going with this? So next time that we meet, what I'd like to do is talk a little bit about this case study here. Prior to the 1950s, the rinderpest was a terrible pest. It was a virus that was impacting cattle and, by proxy, the wildebeest areas in the Serengeti and really all over the world. It's basically like chicken pox for large grazing mammals, and it kills them. Now, the wildebeest got it because cattle in the area were impacted by it. Think about it. If you have a dense population of cattle that have a disease and they're free to roam and graze and mix with wild animals like the wildebeest that you see on the screen, then you're going to have that transmission of the rinderpest virus, and you're going to impact the wildebeest population too, right, as they cross over. But something interesting kind of happened here. There's all of these consequences here in ecology when we talk about this stuff, these unintended consequences. And so how did the eradication and the vaccination for the rinderpest virus in the 1950s that infects both cattle and wildebeest in Africa lead to an increase in tree growth? How is it that when getting rid of that virus that was controlling wildebeest and cattle populations in Africa, how did that ultimately increase the number of trees, the density of trees in an area? It's kind of a fascinating story that we'll get into with our case study that's available on Canvas. I hope this was helpful.